So Rachel is here, right?
Hi, yes.
Rachel, can you share a screen?
Sure. Let's see, can you see that okay?
Yay. Can you move your mouse, do whatever? Yeah, okay.
Okay.
Cool. So I am pleased to introduce Rachel Rosen from Columbia University as our final speaker of this day. She will talk about massive spin-2 fields at high energies, and I'll let you run the show. Rachel, please.
Okay, great. Yeah, thank you so much. It's a pleasure to be here, and thanks especially for accommodating a Pacific time zone. I really appreciate it. What I wanted to talk today is a summary of some work in the last few years about trying to understand massive spin-2 particles at high energies. The question that I am interested in, a question that comes up if you think about massive high spin particles, is can you construct a UV complete theory which has an isolated massive high spin particle in the IR? And the key point here is the word isolated. All right, so we really want a low energy theory where you have just a massive high spin particle and then nothing until some higher energy scale. Now, obviously, UV completions are a very challenging ask. They're a hard ask. And so we can ask a somewhat more modest question, which is, can you construct a low energy effective theory of a massive high spin particle that has a parametrically large separation between the mass and the cutoff? So here you're not worried about the full UV completion. You just want to know from the low energy point of view, can there be a theory with a separation between the mass of your high spin particle and the next state? All right, just so to be very explicit, so we're all on the same page. Indeed, theories of interacting massive high spin particles do exist. So they exist in the QCD spectrum. We have massive high spin hadrons and glue balls where the mass is all set by the QCD scale. They exist in Kaluza-Klein theories. Again, you can have towers of, say, massive spin-2 particles whose mass is set by the radius of the compactification. And obviously in string theory as well, we also have towers of massive high spin particles where the mass is set by the string scale. And now the key thing is that in all of these cases, the masses of all of the other states are parametrically related to the mass of the lowest mass particle in the spectrum. So there's no parametric gap between the states. All right, and so the question that we're interested in is, can the spectrum look like this? So once again, can you have a parametrically large gap between the mass of your lowest mass state and the next state in the spectrum? So we know that we can do this for low spin particles. So for a spin 0 particle, a pseudo Goldstone boson is a nice example of this. For a spin 1 particle, this is precisely what the Higgs mechanism is accomplishing for us. But the question is, for spin 2 and higher particles, can you have a spectrum where the cutoff of your low energy effective theory is higher than the mass of the particle itself? All right, so in this talk, I'm going to focus on spin 2 particles, massive spin 2 particles, for two reasons. So first, they're really the first quote unquote high spin particle. So they're the first particle where these questions become relevant. And secondly, they're interesting because of their possible relevance to gravity. So if you do have a consistent low energy theory of an isolated massive spin 2 particle, you can start to ask questions about cosmology or black holes in these theories. All right, so the outline of my talk is going to be the following. So since it's a somewhat wide audience, I figured I would start by giving a somewhat broad introduction to massive spin 2s in general, what we currently know, and then talk about the two main topics that give us some hint of what UV completions of these theories might or might not look like. So these are related to causality constraints on the theories, and also what we might do to raise the cutoff of the theory as well. So this is all based on work with my terrific collaborators, so James Bonifacio, Kurt Hinterbichler, and Austin Joyce. All right, so first, an introduction to massive spin 2 particles. So what do we mean by a massive spin 2 particle? All right, so let's start with the free theory of a massive spin 2. To write down the free theory, we use the kinetic term for a free massless spin 2 particle. So this is this top line here. This is just the linearization of the Einstein-Hilbert kinetic term. And the kinetic term by itself is invariant under a linearized version of diffeomorphisms. But what we want to do is add a mass to the theory. So we want to add some non-derivative quadratic terms. And there are two such terms that we can write down. The h mu nu term and the trace of h squared type term. All right, and these terms are going to break the linearized diffeomorphism invariance of the kinetic term. All right, and it turns out that we want to write these down in a very particular combination. So we want to write them down in the form of the Fierz-Pauli mass term. And the reason why we want to do that is that when the mass term has this form, it gives rise to an additional constraint in the theory. And this additional constraint is responsible for getting rid of an extra degree of freedom so that the free energy of a massive spin 2 particle propagates the correct 5 degrees of freedom that we would expect. So we would expect a massive spin 2 particle to have plus or minus 2 helicity, plus or minus 1 helicity, and 0 helicity. And this free theory that we've written down here. So there are 10 components of h mu nu. Because the kinetic term has the structure of the linearized Einstein-Hilbert kinetic term, there are 4 Bianchi constraints that eliminate 4 components. And then because we've specifically written down this Fierz-Pauli mass term, there's an additional constraint that removes a 5th component of h mu nu. So we get the 5 correct propagating degrees of freedom. All right, so what about an interacting theory? So we want to think now about a theory of a massive spin 2 particle that allows for self-interactions, which means that we want to add terms that look like h cubed, h to the 4, and higher, and so forth. And so the question is there a nonlinear theory of a massive spin 2 particle that maintains this additional constraint at the fully nonlinear level and therefore avoids this extra pathological degree of freedom? So basically the constraint that we got from the Fierz-Pauli mass term of the free theory, we want to write down nonlinear terms, so interaction terms, in such a way that they maintain this constraint and avoids this extra degree of freedom. So it was argued in 1972 that the answer to the question was no, and in fact there always was a pathological degree of freedom. So it got the name of the Boulward Desert Ghost. So it's only in the past 10 years or so that people appreciated the loopholes in these original arguments. And we're in fact able to write down a fully nonlinear theory of a self-interacting massive spin 2 particle that has this extra constraint and avoids the ghost degree of freedom at all levels. So I wrote it here in a somewhat compact notation. So let me unpack this a little bit. So the first term that appears here, this is just nothing other than the usual Einstein-Hilbert kinetic term. But I'm expressing everything in terms of Vierbeins of the metric. So E is just the Vierbein of my dynamical metric G mu nu. Okay, so all of the potential terms are encoded in this second piece here. It's written in terms of these free parameters, the beta n, which multiply these functions s of n. And these s of n are all the possible ways of taking the wedge product of a Vierbein with a non-dynamical reference Vierbein. So here in these terms, the EA is the dynamical Vierbein associated with the massive spin 2 particle. And this 1 is a 1 form that's associated with it's the Vierbein 1 form of a reference metric in my theory, a non-dynamical reference metric. And because we want these to be Lorentz invariant theories, typically what we do is we take this fixed reference metric to be that of Minkowski space-time, and that guarantees that the full theory of the interacting massive spin 2 particle is in fact Lorentz invariant. All right, so if you're in 4 space-time dimensions, there are only 5 of these terms that you can write down. There are only 5 possible ways of wedging together 2 Vierbeins. The first of these terms is nothing other than a usual cosmological constant term. So this can just get absorbed into the definition of a cosmological constant. Last term, you'll notice, doesn't in fact involve any dynamical Vierbeins, so this term is non-dynamical. So in fact, in 4 space-time dimensions, there are really only 3 new terms that you can write down. And a particular combination of these terms sets the normalization of the Fierz-Pauli mass. So in fact, we can absorb one of the betas into a definition of the mass of the graviton. So if we want to count three parameters in this theory, we have the overall Planck mass, we have a cosmological constant, we have a mass of the graviton, and then there are two leftover free parameters in the theory, which characterize the nonlinear interactions. And once again, this is a fully ghost-free theory. It has a constraint to all orders and only propagates 5 degrees of freedom. All right, so what about the cutoff of the theory? So that's the thing that we're interested in. So first, let's go back just to generic massive gravity, not necessarily ghost-free massive gravity. And if you consider 2-to-2 scattering in a generic theory of massive gravity, and in particular, you look at scattering of the helicity zero mode, what you find is that the high energy behavior of the amplitude scales like energy to the 10 divided by the scale lambda 5. Where lambda 5 is the graviton mass to the 4th power times the Planck mass all to the 5th. Now, if we're interested in a massive spin 2 that has cosmological applications, that means that the mass is going to be incredibly low. So of order of the Hubble scale, for example. So this lambda 5 scale is really a very, very low scale. However, we can do somewhat better than the lambda 5 theory. And it turns out that if you do the same calculation, you consider 2-to-2 scattering of the helicity zero mode for the ghost-free massive gravity theory instead, you get improved high energy behavior. So instead, the amplitude is going to scale like e to the 6th, and the cutoff is going to be given by the scale lambda 3, which is just a geometric mean of the graviton mass squared times the Planck mass. And in fact, it should be said that the ghost-free massive gravity theory was discovered not necessarily by looking for a theory that eliminated not necessarily looking for a theory that eliminates the ghost, but looking for a theory that in fact raised the cutoff of the low energy EFT. And so these two things are one and the same. All right, so sure enough, we're a step in the right direction then to writing down a theory of an isolated massive spin 2 particle where the cutoff of the effective theory is parametrically larger than the mass of the massive spin 2 mode itself. So we have this parametric gap that involves the Planck mass that separates the lambda 3 scale from the mass of the graviton. And it's straightforward to show that this hierarchy is stable under quantum corrections. All right, so just a few words about the scales and the cutoffs that appear in the theory. So massive gravity is like general relativity in that there are two relevant and interesting scales. So one is a scale at which classical nonlinearities become important in the theory. So in general relativity, this is nothing other than the Schwarzschild radius. So if I have, say, some object of mass m, as long as I'm outside the Schwarzschild radius, I can treat the theory not only classically, but also to good approximation in the linear regime. As soon as I'm inside the Schwarzschild radius, I have to take nonlinearities into account, but until I reach the Planck mass, I can still use the classical theory without concern. All right, massive gravity is similar, but these two scales have been pushed to much, much larger distances or much, much lower cutoffs. So in massive gravity, instead of the Schwarzschild radius, you have what's known as the Weinstein radius. So the Weinstein radius is given in the ghost-free theory by this expression here. So outside of the Weinstein radius, you can use the classical theory in its linear approximation. Inside of the Weinstein radius, the classical approximation is still good, but you need to take nonlinearities into consideration. And then once you hit this cutoff of the effective theory, you really need to know what the UV completion of the theory is in order to proceed. And the notable thing about the massive gravity theory is how low these scales are, right? So how large these radiuses are. So for the lambda 3 theory, the ghost-free theory, the Weinstein radius, if I have a source that's, say, roughly the mass of the sun, occurs at 10 to the 16 kilometers. So this is like roughly the size of the galaxy. Whereas this lambda 3 scale is around 10 to the 3 kilometers. So these are really, really very low cutoffs. All right, so an important and pressing question then becomes, what can you do to raise the cutoff of the theory? What can you do to find out more about UV extensions or UV completions of the theory of the massive spin 2 particle? All right, so how can we learn about UV completions or UV extensions of the theory based on low energy information. So we have a few tools in our toolbox. And one of the first things that I'm going to talk about is how to use causality constraints to learn about UV extensions of this theory. All right, so in the S matrix formulation, it's widely believed that causality manifests itself as momentum space analyticity. So actually, I don't have a huge amount of time. I'm going to assume that people are familiar with this and not unpack this slide too much. So it's been known for a long time in this well-known paper that analyticity constraints can be used to put bounds on coefficients of a low energy effective theory. So in this famous example of the d(phi)(4) theory, the analyticity constraint puts the bound on the coefficient of this d(phi)(4) term. And in particular, it tells us that it must be positive. Alternatively, we could consider the same theory strictly from the low energy effective field theory point of view. And we can imagine that we're around some non-trivial background so that this d(phi) term has a VEV, in which case what's going to happen is that the d(phi) to the 4 term is going to renormalize the kinetic term of the theory. And it can be shown also there that C must be positive in order to avoid superluminality around these non-trivial backgrounds. All right, and what's notable is that these two constraints agree with each other. So we have an argument coming from S matrix analyticity. So again, this is supposed to be the manifestation of causality in the S matrix that's telling us that C needs to be positive. And simultaneously, we have an argument about avoiding superluminality in the low energy EFT. And perhaps unsurprisingly, these two things agree with each other. They give us the same bound. All right, so we can ask, is this generic? Is this going to happen for any theory? Is this a coincidence of this d(phi)(4) theory? And in particular, what does this tell us for these interacting theories of massive spin-2 particles? All right, so in a very nice paper by Cliff Chung and Grant Remen, these analyticity constraints were applied to the ghost-free theory of massive gravity. And they use the analyticity constraints to constrain the 2 free parameters of the massive spin-2 particle. So they considered 2-to-2 scattering in the forward limit and applied the analyticity constraints. And here's a little plot. They made a plot in terms of C3 and D5, which you can consider is just a repackaging of these 2 free parameters, the beta2 and the beta3 that I mentioned before. So the white region is the allowed region in the parameter space of massive gravity, whereas the colored region outside is forbidden by these positivity constraints. Okay, so can we do an analogous thing as for the phi-4 theory? And can we check that these constraints are consistent with the absence of superluminality in the low energy theory? There are several subtleties that arise when talking about superluminality in a low energy theory. So you always want to be careful when you're discussing superluminality about whether the backgrounds in questions can in fact be reached dynamically within the regime of validity in the EFT. And similarly, can the superluminality itself be resolved in the effective theory? So these are always subtleties with studying superluminality in a low energy EFT. So one way to kind of circumvent these issues is we can consider the issue of asymptotic superluminality. So in that case, what we're looking at is an S matrix observable, and it doesn't depend on the existence of a non-trivial background solution. So we can consider asymptotic superluminality by looking at iconal scattering. So we're going to look at scattering of the massive spin-2 particle, 2-to-2 scattering in the iconal regime. So this means at large center of mass energy and large impact parameter. And the magic of the iconal regime means that the dominant diagrams contributing to the amplitude all take the form of ladder or cross ladder diagrams. So diagrams of this type. And furthermore, these diagrams can be resummed into an exponential so that the entire amplitude takes the following form. And it can be expressed in terms of what's known as the iconal phase. So this is this function delta SB here, where S is the usual center of mass energy and B is the impact parameter. Now, it's long been known that the iconal phase is related to the time delay or time advance that a particle experiences when traversing a shockwave geometry. So in particular, if delta is positive, the particle experiences a time delay. So for example, if you have a massless particle, it will be moving slower than the speed of light. On the other hand, if delta is negative, then the particle experiences a time advance, and for a massless particle, it would be moving faster than the speed of light. So we can look at the iconal phase to give us some indication of whether or not our theory contains asymptotic superluminality. And again, the advantage is that this is an S matrix observable. We're not assuming anything about having some kind of exotic background in our theory. All right, so the other useful thing about the iconal phase is that it was shown in this somewhat recent paper that in fact it depends only on the on-shell cubic vertices. So the iconal phase depends on the tree level 4-point vertex, which in fact factorizes. And so you only need to know the on-shell cubic vertices of the theory. And this makes it incredibly powerful because even at arbitrarily high energies, there are only a finite number of on-shell cubic vertices that will contribute to this theory. And what this means is that we can study theories of massive spin-2 particles in a model-independent manner. All right, so for the massive spin-2 particle, there are only 5 on-shell cubic vertices. So here I've written them schematically. So there's a vertex that arises just from the potential term from an h cubed term. There's a vertex that arises from the cubic expansion of the Einstein-Hilbert term. So this is a 2 derivative vertex. There's in fact another 2 derivative vertex, which you only get in massive gravity. And this is what's known as the pseudo-linear term. And I'll talk more about this. So this is a kinetic term that is not part of the Einstein-Hilbert structure. In addition, if you're not in 4 space-time dimensions, you also have a Gauss-Bonnet term at cubic order. And finally, the 5th vertex is simply arising from a Riemann cubed term. All right, so this is at all energies. These are the only 5 on-shell cubic vertices that appear for a massive spin-2 particle. And just to be, again, very explicit, so 3 of these you have for the massless spin-2 particle. So Riemann cubed, the Gauss-Bonnet term, and the Einstein-Hilbert term are all there for massless spin-2 particles. So you have 2 new ones for the massive spin-2 particle. That's this pseudo-linear term. And also the h cubed term as well. All right, so what we did is we studied all 5 of these on-shell cubic vertices with free coefficients in front of them. And we calculated the iconal phase for 2-to-2 scattering. And we looked at a regime in which the impact parameter is small compared to the inverse mass of the graviton. And we expanded perturbatively. And we enforced at each level in our perturbation theory that the iconal phase had to be strictly positive. All right, so at the highest order in our expansion parameter, because the iconal phase could depending on the polarizations, on a plus or minus of this term here, we concluded that the parameter A5 was equal to 0. So this kills, this is equivalent to killing the Riemann cube vertex. At the next order, so I should say the equations on this slide here for simplicity are for d equals 4, but we also did this for arbitrary space-time dimensions. So at next order, enforcing the positivity of the iconal phase sets A3 equal to 2A2, which has the effect of killing the pseudo-linear vertex. So this was the non-conventional massive gravity vertex. If you're in higher dimensions at this order, you would also find that A4 is equal to 0. So this kills off the Gauss-Bonnet term. At the next order, you find that A1 is equal to 0. And so what this does is it fixes the coefficient of the h cubed term relative to the Einstein-Hilbert kinetic term. And finally, at the next leading order, when you look at your matrix in the iconal phase, you find that all terms are positive. So it ends here. Okay, I should say that from an effective field theory point of view, all of these coefficients don't need to be strictly zero. The only thing that you really want to enforce is that the superluminality is not resolvable within the regime of validity of the effective theory. But what this means is that even though they don't need to be strictly zero, they still need to be extremely small in order for this to be true. Okay, so the end result of this calculation is that by enforcing the positivity of the iconal phase, this puts constraints on the cubic interaction of a massive spin-2 particle. And again, we did this in a model-independent way, so we didn't assume the DRGT, the ghost-free massive gravity theory, to begin with. And what you find is that the cubic interactions have to take the following form. So you have the Einstein-Hilbert term expanded to cubic order. And then you have relative to that a fixed coefficient in front of the h cubed term. And so the statement is that if the cubic Lagrangian is not of this form, then there must be new physics that arises at the scale of the graviton mass in order to resolve the superluminality issue. But if you do want to be in this regime where you have a hierarchy between the mass of the graviton and the cutoff of the theory, then your cubic interactions need to take this form. Okay, very good. So I said we didn't start out with the ghost-free theory. Nevertheless, these constraints are putting constraints on the interactions of the ghost-free massive spin-2 particles. So these constraints are in fact constraining these beta-2 and beta-3 parameters. And so in fact, we can compare those constraints to the constraints found by Cliff Chung and Grant Remen from the analyticity bounds. So in their paper, if you remember, this was the blue region is the region that's allowed by the positivity constraints. Whereas for these iconal constraints, what we find is an allowed line, which corresponds to C3 equal to 1,4. And this line slices through this positivity blob that they found. So what it means is that if you want a massive gravity theory that's consistent with both of these constraints, you have to sort of lie on this line segment here that's constrained by the blob. But what's interesting is that these, while there is a region of overlap between these two constraints, they don't agree with each other. So it's not the same constraint, the constraint that arises from analyticity and the constraint that arises from the absence of superluminality in the theory. All right, so just to say, there's one more test case that we can look at. So I didn't mention this, but in fact, there's a different ghost-free theory of an interacting massive spin-2 particle that also has this lambda-3 cutoff. And so this is what goes by the name of the pseudo-linear massive gravity theory. So this includes that additional vertex that we discussed earlier. So this theory only has 4 terms. It has the Fierz-Pauli Lagrangian, so it has the linear theory of a massive spin-2 particle. It has this non-canonical kinetic term, and then it has these 2 potential terms as well. So this interacting theory of a massive spin-2 particle, again, it's also ghost-free. It also has this lambda-3 cutoff. However, it doesn't recover general relativity in the massless limit. So when you set m to 0, you don't get back the theory of a free massless spin-2 particle. You don't get back general relativity in the m goes to 0 limit. So you can do these same, you can apply these same constraints to the pseudo-linear massive gravity theory. And there you do find agreement between the constraints, but basically it's a no-go in both cases. So if you apply the positivity constraint to pseudo-linear massive gravity, you find that there's no consistency with positivity. And there's also no consistency for any of the parameters with the absence of superluminality in the theory. All right, so the DRGT ghost-free theory really has the advantage in this regard. All right, so just to end this section with a couple of caveats. So one notable thing is that in flat space time, there's no direct derivation of the absence of asymptotic time advances in the S matrix as a consequence of more fundamental notions such as analyticity or locality. So this is really an additional constraint that we're putting in by hand of the theory. It's not arising in flat space time from more fundamental arguments. And so you could worry that in fact, there might be examples where having this type of asymptotic superluminality may not in fact lead to A causality, may not be pathological. It doesn't seem like that should be the case, but so far there's no rigorous proof that that is actually true. Another concern is that there's no proof that the iconal phase is always given by a resummation of ladder graphs. In particular, you might worry that for subleading diagrams, maybe you don't have the cancellations that you would expect in order for this iconal approximation to be valid. And then the third concern is that the bounds that we derive don't apply for cosmological applications. So here in deriving these bounds, we're of course assuming that we have flat space-time out to the scale of the inverse graviton mass. If you're interested in massive gravitons for cosmological applications, obviously this would not apply as well. Okay. So the final topic that I wanted to discuss was sort of a brute force way of trying to raise the cutoff of the theory. So as we said before, these lambda-3 theories, they have a very low cutoff. And we'd like to know what can we do, not even necessarily to UV complete the theory, but to extend the cutoff of the theory. So can we write down a UV extension of the low energy theory? So when we look at this DRGT ghost free massive gravity theory, and we looked at 2-to-2 scattering of the helicity mode, we said that at high energies, the amplitude scales like e to the 6th, suppressed by this lambda-3 scale. And what we want to consider is whether there's an analog of the Higgs type mechanism for a massive spin 2 particle. So in other words, can you write down a theory where at some high energies you have a massless spin 2 particle coupled to some collection of vectors and scalars? In some regime, the vectors and scalars would acquire a VEV. This VEV would break the diffeomorphism invariance of the theory. And in the low energy theory, you would end up with a massive spin 2 particle. Now, already you might worry that this isn't going to be as straightforward as in the usual Higgs model case, because in massive gravity, the global symmetry that gets gauged to diffeomorphisms is in fact Poincare invariance. And so naively, an analog, a true analog of the Higgs mechanism would involve breaking of Poincare invariance in the low energy phase. Whereas really what we're interested in is there a gravitational Higgs mechanism where the low energy theory gives you a Poincare invariant theory of a massive spin 2 particle? But okay, we can brute force this question to try and find out. So basically what we're going to do is we're going to consider the 2-to-2 scattering of a massive spin 2 particle. And we're going to ask, is there any finite collection of vectors and scalars that we can add to the theory that can be exchanged between the massive spin 2 particles in such a way as to improve the high energy behavior? All right, so can we soften the high energy behavior? Can we lower the cutoff of the EFT by doing this? All right, so we adopted 2 approaches to trying to raise the cutoff. So one was more intuitive and the other one was more general. So I'll start with the more intuitive one to begin with. So the first approach that we took is that we started with the Einstein-Hilbert kinetic term plus an arbitrary potential for the massive spin 2 field. And then we considered all relevant cubic vertices between the massive spin 2 particle and some scalar field. So sorry, I should say some collection of scalar fields, so phi j. And some collection of scalar fields, AJ here. And so for the sake of our calculation, we could put the external massive spin 2 particles on shell, but we left the lower spin particle, which was being exchanged off shell. All right, so this is the most general cubic vertex that you can write down relative to the problem. And then what we did was we simply went ahead and calculated the tree level amplitude. And we considered it order by order in energy, and we fixed the coefficients at each order in energy in order to try and lower or soften the high energy behavior of the theory. And what you find by doing this is that indeed you can recover the DRGT potential, so this ghost-free potential that you find, but you find that there's no possible improvement. That really the behavior, this e to the 6th behavior of the DRT theory is the best that you can possibly get. Okay, but this is not the most general way of approaching this problem. We started with the Einstein-Hilbert term originally, and we added a generic potential. So now we just want to know what is the most general 4-point amplitude that you can write down that's consistent with Lorentz invariance, locality, unitarity, crossing symmetry, and a bounded number of derivatives. And what is the lowest possible scaling behavior for this amplitude? All right. So the approach that we took in this case is that we started by writing down all possible on-shell cubic vertices and also quartic vertices. And the reason that we are able to use on-shell cubic vertices is that any term that vanishes on-shell will show up later in the quartic vertex via a field redefinition. So this was helpful because being able to use on-shell cubic vertices meant that there was only a finite number of free parameters for the exchange term. Whereas for the quartic vertices, there's a finite number of tensorial structures that you can write down that get multiplied by free polynomials of the Mandelstam variables. So again, for the cubic interactions, we have a finite number of free parameters. And for the contact terms, for the quartic vertices, we have a finite number of free polynomials. So again, it's a similar procedure. You compute the amplitude, you expand at high energies, and you fix the coefficients order by order. So the free polynomials get fixed in terms of the free parameters of the exchange terms and so forth. And what you're left with is a bunch of sum rules effectively for the coefficients of the on-shell cubic vertices. And sure enough, in this model independent way, you also find that there is no improved behavior. So there's no way of picking a finite number of scalar fields and vectors in such a way as to improve the behavior of the massive spin-2 amplitude. Okay, so the conclusion is that raising the low cutoff of the massive spin-2 particle is going to require massive particles of spin-2 or higher. So this is perhaps not surprising. This is what people have always believed in the literature, and other people have argued to be true. What's notable here is that we weren't even looking for a UV completion of the massive spin-2 particle. We were really just looking for a UV extension. So something just to get us to some higher energy scale. And even to find a UV extension, there's no such thing as a gravitational Higgs mechanism unless you start to include massive particles of spin 2 or higher. Okay, so obviously, again, we do have UV complete theories that contain massive spin 2 particles in them. But the outstanding questions would be, is it possible to raise? So all of these theories involve an infinite tower of massive high spin particles. And so the interesting questions would be, is it possible to raise the cutoff of the theory with a finite number of particles? Or once again, we're still left with the open question, can you have a parametrically large gap between the mass of the massive spin-2 particle and the new physics that appears in your theory? So I think I'm out of time, so I'll stop here. Thank you.
Okay, Rachel, thank you. Let's thank Rachel for this very intriguing talk. And I'll open the floor for your many questions, hopefully. So either unmute yourself or raise your hand. So Nima, Lance. Okay, let's start with Lance because he's first.
Okay, thanks a lot for a very interesting talk, Rachel. Can you talk about this statement that this small mass is stable under quantum corrections? On the one hand, there were these very high growth with the energy of the 4-point amplitude. So you might have thought if you just hook those around, you get a big mass. What's the symmetry that protects the mass from it?
Yeah, so it's because you have a diffeomorphism invariance in the m goes to 0 limit that makes it technically natural.
So it's a gauge symmetry rather than a kind of global symmetry that is causing the naturalness.
That's correct. Yeah.
Thanks.
Sure.
Okay, so Nima, go ahead, please.
So I have two questions. One is kind of a general one, since I have not kept up with this topic. Back when we looked at these things in 2002 with Matt Schwartz and Howard Georgiev, we found this lambda 5 behavior for the Pierce-Pauli theory, and we saw that you could not do better than lambda 3. And that you have to modify the theory with nonlinear corrections in order to get it to lambda 3. And actually, Matt Schwartz had a very nice amplitudes-based paper already back then that proved that you could not do better than lambda 3. What's the sort of new thing in the DGRT story? Is it just a sort of further full nonlinear completion of that to show that you get lambda 3 beyond 2-to-2 scattering? I mean, ultimately, what we did not know at the time was that these things are controlled by the Galilean symmetry for the extra longitudinal modes. So that's something that we didn't know, and the DGRT construction does have the Galilean symmetry. That's the sort of, as far as I understood from 10 years ago, was the sort of symmetry basis of these things. But yeah, can you say what the addition is with the more with the developments from 2010 that was beyond the knowing that you could do as well as lambda 3?
Yeah. So you're absolutely right. The statement about lambda 3 itself has not changed. What was argued after that was that these theories still inevitably contain ghosts. So it was believed that the classical theory was always ghostly, even the lambda 3
you mean because of that
theory.
wrong paper that was written?
That's correct.
Right,
Yeah.
Right. That was okay. Right. That was a paper doing an incorrect analysis of the model that we talked about.
That's right.
So it was the realization that there are no ghosts even around finite backgrounds. I mean, the business about finite backgrounds is what needs the full Galilean symmetry in order to understand. Is that right? Am I understanding?
Yeah,
correctly?
that's correct. Yeah. So they, that's correct.
Okay, right. Okay, good. So I just wanted to understand that. But there's a second. There's a more. There's another point I'm sort of super confused about at 0th order from your talk. So I must be missing something. Thinking about massive gravity was a huge motivation to the paper we wrote about superluminality and so on. And of course, back then, again, we didn't realize this connection between the Galilean symmetry and ordinary massive gravitons, but theories with the Galilean symmetry for the scalar field were there already in essentially massive gravity a la DGP that I'm sure you know very, very well. And sort of part of the motivation of our paper was realizing that exactly that Galilean symmetry demanded the absence of the 4 derivative terms that forced the existence of superluminality and forced the absence of the S squared terms in the amplitude that would violate the positivity bounds from dispersion relation. And it doesn't have seem to have anything to do with any technicalities of whether you define it in the S matrix or this or that. It's you have this extra degree of freedom, this extra scalar degree of freedom, and you just look at how you source it around the sun, and in that background, you can send signals like √2 times faster than the speed of light, and you can reach out and touch someone far away, right? Where did all that go in your presentation? I didn't, here you're saying there's some regime where everything is healthy and so on, whereas our conclusion was sort of radically the opposite, that the second you go to distances small compared to the Compton wavelength of the graviton, or high energies, high just compared to the mass, but well beneath any of the other scales that you're talking about, that you're just dead in a regime where you see superluminality. So, how is that observation consistent with what you were saying today? It's a very good question. I just must have missed something. Is what's going on? Do you have much weaker couplings or something like that, or what?
Yes.
Yeah, can you explain what's going on?
So I should have said, but the basically you can think of massive gravity as being like an IR deformation of the Galilean theory. So it's true that you can start with massive gravity and you take this high energy limit and you end up with a Galilean theory, and then everything that you're saying holds true. But if you deform that theory in the IR, it actually modifies these positivity bounds in a way that gives you this bubble that Cliff Chung and Grant Remen found.
That's so I see. But you have a sort of a cutoff, sort of somewhere near where the mass of the graviton is, or something like that. Is that right?
No, there's no. The cutoff is still yeah.
Maybe I'll just say again what I'm confused about. The second you go to energy is high compared to the mass of the graviton, I would have thought that there's an effective theory which is just given by the, there's the transverse modes of the gravity we forget about, and there's just the massless Galileon, and then you get what you get from that Galileon, which is superluminality. So why is that argument wrong?
Yeah, so again, I would say it's really because you are changing the theory in the IR, and these positivity bounds are sensitive to that it changes the constraints of the theory.
Okay, well, maybe we can talk about it more offline, but it's a very zeroth order thing. Like, can you go √2 times faster than the speed of light around the sun? Right, that's the question. And what is the answer to that question? Yes
so
no?
I would say no, as long as you're within this bubble.
But are you within that bubble for reasonable masses? Like, let's say for Hubble mass.
Yeah, sorry. So the parameters are independent of the mass of the graviton. So there are two additional free parameters that control the higher order interactions in the theory. So yeah, you can have a Hubble scale graviton mass and still be in this bubble.
Okay, all right, thank you.
Yeah.
Rachel, maybe I'm missing something, but could it be that the analysis between the more recent works to 10 years ago, it was just more model independent in terms of the Onshell cubic vertices and so on and so forth?
Yeah, so that's certainly true of this this attempt to raise the cutoff. But this positivity bound is really, I think, just sort of turning the crank using the same machinery that people were using previously, but for the massive spin 2 particle. I'm not sure how much that part has necessarily benefited from more modern technology.
Okay.
Yeah.
So I see. So Nima, you're done? Yeah, I think so. Simon, please.
Yeah, thank you. Sorry.
I guess I can wait for the discussion session, which is now, right?
We still have time.
Okay, great. Okay. I asked my question then. Yeah, it's also about the relation with the Galilean theory. Right. If correct me, I haven't followed this massive gravity story very closely either, but the E6 behavior is because you have a scattering amplitude for the elasticity zero mode that goes like STU. That's this thing, right?
That's right.
And below that, do you have something that goes like energy the fourth that would be like, S square plus dot dot dot?
Yeah, so there are other helicity modes. Yeah.
Sorry. No, for the elasticity zero mode.
Oh, so sorry. Say your question again.
Yeah, because when people talk about the Galilean theory, they often talk about the theory where this energy, the fourth term, is fine-tuned to zero, basically, or ordered is like suppressed with similarly to with the mass. Is you're talking about this theory?
No, I'm not super familiar with that claim. Okay. Yeah, maybe somebody else is, but yeah.
Yeah, because there are results that exist now. You may be interested in the paper by Tolle, Zhu, and Wang from last fall. I will put the reference. There are bounds on the ratio of they're bound. They're basically like the S matrix bounds, but the analysis of this matrix doesn't just give you positive within the forward limit. There's infinitely many more constraints one can get from this approach.
That's right.
So there are constraints on the coefficient of the energy to fourth, energy to six, and effectively it's impossible to fine tune the energy 4 to 0.
Okay.
So yeah, I have not followed this story closely, so I cannot say if this rules out this model or not, but seemed relevant.
I see. Yeah, I haven't seen the paper. I would have to look more closely at it.
Okay, thanks.
Cindy, please go ahead.
Hi there. My question actually might be related to Simone's, and Simone, you can tell me if it's basically the same question or not. Sorry if it is. I was just wondering how the causality constraints that come from the sum rules and crossing symmetries that Simone was talking about in his talk on Monday, how they affect this theory. Is that basically the same question, Simone?
Yeah.
Okay. Then in that case, if you have input, Rachel, I'd like to hear about it.
Well, so I mean, okay, I can say what I know, which is that so there are, people have looked at enhanced positivity bounds applied to these theories. And in fact, the papers that I'm aware of it's an older paper by Andrew Tully and Claudia Duran, and also by Bellazzini. And what they show is that because you have softer scattering in the forward limit, that you actually get a stronger constraint. And it seems to imply, and they don't say this explicitly, but if you work through what they're doing, what it seems to imply is that the actual cutoff of the theory might be the lambda-4 cutoff rather than a lambda-3 cutoff, which is an even lower cutoff of the effective theory. So the lambda-4 cutoff goes like graviton mass squared times m Planck squared all to the 1/4 power. So my only familiarity with these sort of improved positivity bounds is that they seem to be suggesting that the actual cutoff of the low energy effective theory might be even lower than this lambda-3 scale. But this doesn't rule out the theory because it just means that you really do need to know what the UV extension of the theory is. It just makes the region of viability of the theory much smaller.
I think their claim of the paper last fall is that the region of validity is empty because the cutoff has to be the same as the mass of the graviton.
Okay, I should look at the paper. I haven't seen it.
Okay, thanks.
This was essentially my comment that that you can't go parametrically above the mass of the graviton, because if you do, you're dominated by the perfectly Galilean symmetric limit of the massless Galileon, and then you get what you got before.
So I would disagree with that for the, I would disagree with that for the lowest order positivity constraint. It could be that the higher order positivity constraints are showing this.
But really, I mean, sorry, just say that this is not some technical issue about what positivity constraint. It's really, can you reach out and touch someone? I mean, if the e to the 4th terms are small, relative to the e to the 6th terms, there's a large range of distances where the superluminality is just nakedly visible in your face, as it was when we talked about it back then. I don't see how this is something that can sort of be saved by turning on a small.
I think Nima, correct me if I'm wrong, but if the quotient of E6 is large and negative, they may be
Nope,
may have been an exception. The sign didn't matter to you?
Nope.
Okay.
Okay, we'll cut this very interesting discussion just at the right time to continue it in another place in Gathertown. Before that,